Hello students, how are you? I hope you are well. I welcome all of you on this educational platform. In this unit, structure of atom, in the previous classes we discussed about the fundamental particles, cathode ray, anode ray, and also about the structure of atom, some basic models like Bohr model and Rutherford's model. In today's class, we shall discuss about some modern theories. Today we shall discuss De-Broglie hypothesis, or you can say De-Broglie dual nature of matter. In this, we will discuss about the De-Broglie waves. After that, we shall discuss about the Heisenberg's uncertainty principle. So, what is uncertainty? What is the Heisenberg uncertainty principle? Now, we will discuss in this unit. So, let's proceed. This is our today's discussion about De-Broglie waves and Heisenberg uncertainty theory. Moreover, in this class, I will tell you something about the modern concept of atom. So, in the previous classes, we studied about the Rutherford's model and Niels Bohr model. In this class, we shall discuss about the modern model of atom, which is also called as quantum mechanical model. This model, students, is the widely accepted model. As it is the modern model, it is the most widely accepted, and it is based upon the quantum mechanics. It is not based upon the Bohr's theorem, it is based upon the quantum mechanics. And it was developed by the scientist named Erwin Schrödinger. The name of scientist was Erwin Schrödinger. He explained the concept of dual behavior. You know what is exactly do we mean by the dual behavior? When particles show double behavior, means they behave as a particle and also as a wave. Say for example, right now I am not in front of you, but you can hear me. So I am not a particle for you. You cannot touch me, you cannot see me, but you can hear me. So here at this moment, at this very moment you are attending this class, I am wave for you. So now I am behaving as a wave. In case, suppose you imagine I am teaching you students right in front of you. In that case, simultaneously I show particle and wave behavior. So that we shall discuss in the dual behavior of matter and Heisenberg's uncertainty principle. I am pretty sure you must be aware what is uncertainty. See, when things are not certain, when they are not certain, they are uncertain. Alright, suppose you are rolling a dice. You are playing a game and you are rolling a dice. Before throwing the dice, do you know what would come? Nobody knows. From 1 to 6, any number might come. So that is uncertain. But once you throw the dice and say for example number 2 came, then there is no uncertainty. Now it is certain that 2 came already. So sometimes things are uncertain and sometimes they are certain. So what do we mean by uncertainty here in this chapter? That I will tell you. But first we will study about the dual behavior of the matter. So what is the dual behavior of matter and what is Heisenberg's uncertainty principle? And then we shall discuss the main features of the quantum mechanics model. So do you understood what we will gonna study today? First we shall study about the dual behavior of matter and also Heisenberg's uncertainty principle. Then I will tell you about the main features of the QM model, that stands for quantum mechanic model. So here we go students with the dual behavior of matter. In this picture you see a person named Louis de Broglie. So Louis de Broglie in 1924 he proposed that matter, what is matter? Anything which have mass and occupy some volume is called as matter. So in 1924 students, he proposed that matter should exhibit dual behavior, means particle and also wave-like properties, just like radiations. Radiations are wave. So he proposed this concept that matter should also behave or also exhibit two kind of behavior, particle and wave. He was a French physicist. and he gave the concept of, please remember this name, dual nature of matter. Please remember this name, students. It is dual nature of matter, and he was awarded Nobel Prize in Physics in 1929. And see, we are studying this topic in chemistry. He was awarded Nobel Prize in Physics. So this is De-Broglie equation. This is how De-Broglie equation exactly look like. I'll tell you. Suppose a material particle having a momentum p. You have a material particle for which momentum is p, which correlate particle and wave nature. See, wavelength is the property of wave. So this represent wave nature, while p is the momentum, and momentum is equals to mass into velocity, and mass is the property of particles. Waves do not have mass. Particles, they do have mass. So this represent particle nature. This represents particle nature. Now we can understand why this equation is called as connection between dual behavior, because it correlate wave nature and particle nature. In this equation, this h is the Planck constant we already studied in the previous classes, and the value of h is 6.6 into 10 to the power minus 34. And this momentum, this p is the momentum, which is equals to mass into velocity. So if you replace this value lambda, you can also write the equation lambda is equals to h upon mv. Alright. Now this is the first equation of De-Broglie. Lambda is equals to h upon, say for example, I say that p is equals to mass into velocity. Now you can replace this momentum by mass into velocity. So the another formula of lambda will be h upon mv. You can also use this formula for calculation of De-Broglie wavelength. Do you know, students, what is kinetic energy? Let me tell you that kinetic energy is half mv square. Most of you students already knowing this formula. Now if I multiply this formula by m and divide by m, it will not make any impact. Multiplied with the m, divided with the m, they will cancel out each other. There will not be any impact, and it will be m square v square divided by twice of m, where p is equals to mv. So if I use m square v square, it will be equal to p square. So now I will replace this value. Now kinetic energy, I will say kinetic energy is equals to p square upon twice of m. By this equation you will get the value that momentum p is equal to twice m kinetic energy to the under root. Now in this basic formula of De-Broglie wave, now I shall replace this p with the kinetic energy formula. So the another formula of lambda will come. Lambda is equals to h upon twice of 2m kinetic energy. So here is the another formula for the calculation of De-Broglie wavelength, students. This is the formula in terms of momentum. This is the formula in terms of velocity, and this is the formula in terms of kinetic energy. Alright. Now, do you know what is kinetic energy? Kinetic energy of charged particle. What is the kinetic energy of charged particle? Under the influence of some potential, in the presence of electric voltage. For any charged particle, kinetic energy is equals to Q into voltage. So now I can also replace this kinetic energy with the Q into voltage. So here comes the another formula of De-Broglie wavelength. Lambda is equals to h divided by 2m Q into voltage. So you can use any of the formula. This is number 1, number 2, number 3 and number 4. You can use any of the formula for the calculation of De-Broglie wavelength. And now I will tell you about some features of De-Broglie concept. So according to De-Broglie, always remember, students, that according to De-Broglie, any moving particle, some waves are associated. Please do take care that I use the word associated. I'll tell you why in some time. With any moving particle, some waves are associated called as de-Broglie wave. They are called as de-Broglie wave. Now students, why I am saying associated? See, when you speak, when I speak, our voice comes out of our mouth and it travels from one to another place. When you say something, person standing near to you will listen what you are saying, because the sound waves which comes from your mouth, they travel. They are not associated with you. They are released from you. See, there is a difference between association and release. Sound waves are released from our mouth, so they travel. But de-Broglie waves, they never release from the particle. Students, this is important. They remain associated with the particle. They always remain associated with the particle. So they are stationary wave. They are stationary wave, means they do not travel from one to another place. They are not released. These waves are not emitted. Alright. These waves are not related with the energy. I will never gonna ask you that what is the energy of de-Broglie wavelength. No. Yes, I can ask you kinetic energy of the particle from which or along which de-Broglie waves are associated. But I will never gonna ask you, we will never ask you what is the energy of de-Broglie wave, because they are not related with the energy. Alright. And remember, these waves are also called as probability wave. Do you know, students, what is the meaning of probability? I am pretty sure you must be knowing what is the meaning of probability. Probability is the chances. See, say for example, you are sitting in any room. Door of the room is closed and you heard, all of a sudden you heard a human voice which comes out of the, somewhere out of the room. What you will imagine? What you will think? Definitely you will think that there must be some human or any person outside my room and who is talking to another person. Have you seen that? No, you haven't seen them. But still, you are saying that there must be a person outside my room because you heard a voice. So whenever you heard a voice, there is a probability. There is a probability. There is no guarantee, but there is a probability. There are chances of presence of someone. Similarly, in any given space, suppose you see some de-Broglie waves are there, which simply represent, if some de-Broglie waves are there, they simply represent the presence of some moving particle there. So there is always a probability of finding a particle when de-Broglie waves are there. So they are also called as probability waves. Right, students? So this was something about the de-Broglie theorem. There was something about the de-Broglie concept. Now I will tell you about the Heisenberg's uncertainty principle. So here is the Heisenberg's uncertainty principle. Here is the picture of Heisenberg. He was a German physicist and he also awarded the Nobel Prize in Physics in 1932 for the concept of quantum mechanics. Because of the concepts he gave in the quantum mechanics, he was awarded Nobel Prize in 1932. Alright, now here we go. See, what is the Heisenberg's uncertainty principle? Like I told you, students, whenever I say uncertainty, means when things are not certain, they are uncertain. Like I gave you the example, whenever you throw any dice. So whenever you throw any dice, what will come is always uncertain. Similarly, he says that it is impossible, it is not possible to locate position of electron and calculate momentum of electron simultaneously with accuracy. Means there will always be some error. There will always be some error in calculation. Means whenever you will try to find out momentum of electron as well as position of electron, you would not be able to do that with the certainty. There will always be some uncertainty or error in that, and that is called as uncertainty in the calculation. So here delta x is the uncertainty in calculation of position. Whenever we calculate the position of electron, there is some uncertainty, and that uncertainty is called as delta x. What is delta p? Delta p is the uncertainty in momentum. So this is uncertainty in momentum of electron. Students, you already know that momentum is equals to mass into velocity. Momentum is equals to mass into velocity. So change in momentum or uncertainty in momentum is equals to m delta v. Why? What is delta v? Delta v is the uncertainty calculation of speed of electron or velocity. So this is delta v. There is no uncertainty in mass because mass is always certain. Let me give you an example. Suppose you have mass 50 kilograms, okay, and you are sitting in front of me. Now your position is certain to me. I know where you are because you are right in front of me. And then you say goodbye. You say that, sir, I am going now, and you leave the premises. So when you leave the premises, now where you have gone, I don't know. I don't have any information of your whereabouts. So now your position is uncertain to me. Now if somebody asks that where is Mr. X, I don't know. He might be downstairs, he might be outside the building, he might be within the building, that I don't know because now he is not in front of me. So now his position is uncertain to me. Definitely it is uncertain. But that I know, wherever he is, mass will be 50 kilogram because your mass not changes with your position. Suppose in any building you are at the second floor and your mass is 50 kg, and if you travel to the third floor, your mass will remain at 50 kg only. Although there is a change in position, but mass will remain same. So there is no change in mass, but there is a change in momentum, there is a change in velocity, there is a change in position. So delta v is the uncertainty in the calculation of velocity. Alright, now according to the Heisenberg uncertainty principle, multiplication of the uncertainty in position and uncertainty in momentum is greater or equal to h upon 4 pi. Also you can say that delta x dot m delta v, if you replace momentum with the speed, greater or equal to h upon 4 pi. These are the formulas given by Heisenberg in the uncertainty principle. Now what is the significance of this principle? The uncertainty principle is used, this uncertainty principle, students, you see, is used to determine the definite path of the moving object or the trajectories. If you want to know the information of the trajectories or the path of the moving object, we use the uncertainty principle. The fixed path of an object is find out by its position and also the velocity at the various moment. So if we know the position of an object and its velocity and the force acting on it at a particular instant, any given time, then we can find where the object would be sometimes later. By calculation of the quantum mechanics model and the forces, we can predict where this object would be after some time. So we have an idea about the trajectories, as I told you. Now the next thing which comes in front of you is the Schrodinger's wave equation. Definitely it was given by the Erwin Schrödinger, and this is quantum mechanics equation which is in front of you. In this equation, this H naught is Hamiltonian operator which is used to solve this equation. Psi is the wave function of electron, psi is the wave function, and E is the energy of the system. E is the total energy of system and psi is the wave function. Alright, when h operate on psi, the result of such operation is energy of the system along with the psi. So what is psi? Psi is the wave function, and this quantum mechanics equation is the relation between total energy of the system and wave function. And why it is used? What is the significance? What are the features? See, with the help of quantum mechanic model, the main feature we gave that number one, energy of electron is quantized. I already told you about the concept of quantization in the previous classes. Quantization means when something is found in the multiple of some integer value, lowest common value, then it is called as quantization. If you solve the Schrödinger equation, it will give you the energy values for the quantized level. So what is the energy value for the first quantized level, or for the second quantized level, or for the third quantized level? You will get the value of energy, and it does not specify the exact position and the momentum of electron as Heisenberg's uncertainty theory, but it focuses on the most probable reason, students. Here we never say that electron is present here with the certainty. Here we focus on the most probable reason, where the probability of finding electron is maximum, and those places where probability of finding electron is maximum are called as probability density, which I'll tell you. An electron in each orbital has a definite amount of energy. We know already, we studied that in the Bohr's model. So whenever an electron is described by a wave function psi, suppose you are representing electron by the wave, then this maximum displacement from the mean position is called as psi. It means that electron occupies an orbital. So when you represent the psi, it means electron occupies an orbital. And the probability, important students, the probability of finding an electron at a point within atom is proportional to psi square, and this psi square is probability density. So what is the probability? What is the percentage chances? What is the probability of finding electron in any species? That is called as probability density. So this psi square is called as the probability density, and it is always positive. It can never be negative. Maximum value of the psi square is for orbital, and minimum value is 0 for nodes. In the coming classes, I'll tell you about the nodes. Nodes are those places where electron never found. So where the probability of finding electron is absolutely 0. Those are called as nodes. So for nodes, the value of psi square is absolutely 0. And it is maximum, psi square is maximum for orbitals, because probability of finding electron is maximum for orbitals. Now if you solve this wave equation, students, which is not in your syllabus, of course, solution of this equation is not in your syllabus. So for the solution of the wave equation, it will give you 3 constants which are known as quantum number, which I'll tell you about quantum numbers in the next class. And the quantum number gives the complete information regarding the position and the energy of electron. You can say that quantum numbers are like the address of electron. They give you complete idea of electron in an atom, where it is, what is the position, what is the energy. This is represented by the quantum numbers. Now in the last of this class, I'll tell you something about the orbitals. So what are the orbitals? They are the region in space around the nucleus where the probability of finding electron is maximum. I told you orbitals are the places for which psi square is maximum. Definitely it is not 100% as per the Heisenberg, and it represents the total volume where an electron spent most of its time, because its finding probability is maximum. So students, this was about the modern model of atom, which includes De-Broglie, Heisenberg and Erwin Schrödinger's quantum mechanics model. In the coming class, I'll tell you about the quantum numbers, which is quite interesting. So I'll see you in the next class. Till then, goodbye and take care. Please keep on coming and keep on watching us. Good luck.